Welcome, everyone. Get ready, because today we're taking a journey far, far beyond what the human eye can actually perceive. In this explainer, we're going to explore the absolute bleeding edge of microscopic imaging. We're stepping into a realm where the fundamental building blocks of materials, electronics, and honestly, even life itself are laid completely bare. So get comfortable, focus in, and let's embark on an incredible journey to the nanoscale.
It all really starts with a fundamental challenge. Pose this to yourself. How exactly do we see the completely invisible? Our human eyes are biological marvels for sure, but they have a hard limit. Even traditional optical microscopes, the kind you probably used back in high school biology, eventually hit a brick wall dictated by the wavelength of light itself. To truly understand modern engineering, medicine, and chemistry, we have to look much, much deeper. We need a tool that absolutely shatters those traditional limitations.
And that brings us to this staggering number, 1 million times magnification. Just let the sheer scale of that wash over you for a second. We aren't just talking about making a tiny cell look the size of a coin. No, we're talking about zooming in so incredibly close that we can literally map the exact surface texture of a single isolated virus, or trace the impossibly thin electrical gates hidden inside your smartphone's processor. This is the awe-inspiring magnification power of the technology we're unpacking today.
Okay, let's dive into this. Here is our agenda for today. 1. Meet the FES. 2. Nanotechnology and Materials Science. 3. Electronics and Semiconductors. 4. Biological and Chemical Research. And 5. The Big Picture.
Moving to Section 1. Meet the FESEM, the ultimate nanoscale lens.
So, FESEM stands for Field Emission Scanning Electron Microscopy. I know that is quite a mouthful, but the core concept is actually brilliantly elegant. Instead of bouncing regular light off a sample to see it, this specific microscopy technique utilizes a highly specialized field emission electron gun. Think of it like painting the surface of an object with an ultrafine stream of electrons instead of just washing it with broad beams of light. Because electrons have much, much shorter wavelengths than visible light, we get to bypass the limits of traditional optics entirely, providing ultra-high-resolution imaging and precise structural analysis.
So why do top-tier modern labs rely so heavily on FESM? Well, because it completely solves the bottlenecks of older imaging tech. Just look at these core features. First up, we get ultra-high resolution, down to roughly 1 nanometer. It also offers a surprisingly large depth of field, meaning the resulting images have this incredible 3D-like quality and just phenomenal image clarity. Crucially, it features low voltage operation, and it boasts excellent surface sensitivity. It doesn't just show you that something is vaguely there, it shows you exactly what its surface feels and looks like.
And this brilliantly illustrates how the FESEM is the undeniable nexus for modern multidisciplinary science. It sits right there as the central hub for innovation across nanotechnology and materials science, electronics and semiconductors, and biological and chemical research. The FESEM isn't just some niche tool. It's literally the engine driving massive breakthroughs across these entirely distinct domains.
Section 2. Nanotechnology and Materials Science. Engineering the micro-world.
Now, over in materials science, the FESM acts as both an incredible camera and an ultra-precise microscopic ruler. Scientists are using it for visualizing complex nanomaterials, things like individual nanoparticles or carbon nanotubes. They use it for directly measuring the dimensions, actively sizing nanoscale features to ensure they were manufactured correctly. It's also vital for studying thin films, so checking the exact thickness of microscopic coatings, and for surface morphology analysis, giving engineers a really up-close look at the texture, porosity, and grain structure of brand-new synthetic materials.
So the crucial point is grasping the sheer scale we're dealing with here. Just look at this measurement, 50 nanometer nanowires. To put that into perspective, a single sheet of everyday printer paper is about 100,000 nanometers thick. The FESM is smoothly and clearly imaging structures that are functionally invisible to us, allowing researchers to measure and shape these incredibly tiny wires with absolute pinpoint precision.
And it's exactly the same story for thin films. Being able to measure a coating layer that's just 120 nanometers thick is absolutely vital. When you're engineering advanced materials, say maybe a new hyper-efficient solar panel coating or a thermal protective layer for aerospace equipment, surface uniformity is everything. The FESEM perfectly checks that these ultra-thin coatings are flawlessly applied across the entire surface.
Moving right along to Section 3, Electronics and Semiconductors, powering the modern world.
You know, microchip manufacturing is easily one of the most exact and unforgiving processes on Earth. There is zero room for error, which means the FESEM is completely non-negotiable here. It's used for evaluating super complex integrated circuits by looking right at semiconductor cross-sections. It's the ultimate tool for defect analysis, effortlessly locating tiny faults that would otherwise totally ruin a processor. It also runs contamination checks to find impossibly small unwanted particles on those microchips and performs layer thickness measurements for thin films and inner layers. These four capabilities are absolutely vital for quality control and for keeping Moore's Law alive.
To really put that into perspective, chip manufacturers are currently using FESMs to inspect gate widths and oxide layers that measure just 100 nanometers across. When a modern microprocessor has billions of tiny transistors, a microscopic defect on a single 100-nanometer gate can cause a catastrophic failure. The FESM acts as the ultimate quality assurance inspector, diving deep into the silicon trenches to make sure every single nanoscale component is flawlessly constructed.
Section 4. Biological and Chemical Research. Unlocking Organic Mysteries.
Now, what's really interesting about this slide is a core technical difference that makes biological imaging actually possible in the first place. See, standard electron microscopes often rely on high-voltage imaging. That's fine for a silicon microchip, but it causes heavy, destructive damage to delicate, beam-sensitive organic matter. The absolute secret sauce of the FESEM is its low-voltage imaging capability. This allows researchers to perform safe, high-resolution analysis of highly sensitive organic samples without blasting them into oblivion with heavy radiation damage.
Because of that crucial low-voltage capability, the FESM is a total game-changer for biological research. Scientists can now view the detailed topographies of complex cellular structures. They can capture high-resolution imaging of microorganisms, we're talking bacteria, fungi, viruses, and observe them in their natural structural states. It's also perfect for analyzing the surface morphology and structure of delicate polymers and biomaterials. Being able to view these topographies without destroying the sample in the process, that opens up entirely new frontiers in medicine and chemistry.
I want to bring you back to this mind-bending statistic one more time. Approximately 1 nanometer resolution. When applied to biology, this means we can literally see the intricate armor of a virus or the complex folded surface of a cellular membrane with absolute undeniable clarity. We are intimately observing the very building blocks of life and the root causes of disease at a scale that was entirely unimaginable just a few decades ago.
Let's move to Section 5 and see how this builds into our concluding summary. The big picture, a closer look at the future.
Ultimately, as this says, the FESEM enables ultra-high-resolution imaging and precise analysis of surfaces and nanostructures across a wide range of scientific and industrial applications. It's not just a fancy camera, it is the foundational bridge between human curiosity and the nanoscale universe. Whether we're trying to cure a new disease, build a radically faster computer, or engineer stronger, lighter materials for space travel, the FESEM is the tool that lets us verify our work and truly understand our world.
And that leaves us with this final, genuinely exciting thought. We've pushed the boundaries of magnification to 1 million times. We can map a virus and measure a 50-nanometer wire. So what breakthroughs will we discover next, now that we can finally see, measure, and interact with the fundamental building blocks of our world? It's a thrilling question, and I hope this explainer has given you the perfect lens to view the answer. Keep learning, keep focusing on the details, and we'll catch you in the next one.